Hello class, welcome to the Stat 215 Lecture 16 video. In this video, we are going to understand the concept of sampling distributions. We will specify the sampling distribution for X bar, or the sample mean. We will learn about the central limit theorem, and we will use the central limit theorem to find probabilities about our sample mean. Let's begin by looking at our first objective, understanding the concept of sampling distributions. In order to understand our first objective, let us first review the difference between population and a sample. So for us, a population is the complete set of people or things being studied. For example, all the registered voters in the United States. A sample would be the set of people or things from which data are actually obtained. So this could be when the news stations call random people and ask who they're voting for. They're taking a sample of our population. Now, to have an understanding of our first objective, we first need to understand that each observation in a population is a random variable x that takes on values according to some probability distribution f of x. So when we refer to a normal population, we mean a population whose observations are values of a random variable having a normal distribution. We could do the same thing for a binomial population or any population of f of x. This leads us to talk about what is a random sample at all. So in selecting a random sample of, say, size n from a population f of x, we define random variable xi, where I equals 1, 2, all the way to n, to represent the ith measurement or sample value we observe. So the random variables x1, x2, all the way to xn constitute a random sample from the population f of x with numerical values x1, x2, all the way to xn. And x1, x2, all the way to xn are going to be independent of each other with the same probability distribution f of x. And because these are independent, we know that f of x1, x2, all the way to xn is going to be equivalent to f of x1 multiplied by f of x2, keep on multiplying all the way to f of xn. So just to be clear, because I have had a couple questions about this, about the difference between capital X and lowercase x. So for us, our x1, x2, all the way to xn, that is capital X1, X2, all the way to xn, these are each a random sample. And within each of these samples, they have observations x1, x2, all the way to xn. Now this is the lowercase x. So here, I'll try to make that look a little bit different for you to understand, a little bit easier. Again, so capital X those are each a random sample from the population. And we can take multiple samples from a population. Imagine we're asking about, say, your favorite sport at WVU. We could go to different campuses at different times and each time ask, say, 20 random people and then look at our results. So we would have a bunch of random samples from our random locations at a random time. And each of our observations in those samples would be our lowercase x1, x2, all the way to xn. So to help us understand sampling distributions a little bit better, let's take a review of the sample mean. You'll see why later. So let x1, x2, and all the way to xn represent n random variables. So this means that capital x bar will equal 1 over n multiplied by our summation of I equals 1 to n of capital Xi. The statistic, capital X bar, or again, this is a sample mean, assumes that the value, lowercase x bar, equals 1 over n multiplied by the summation of I equals 1 to n of lowercase xi. And this is when capital X1 equals small x1, and so on. So for us, when we say sample mean, this refers to both our statistic and our computed value. So now that we've reviewed our sample mean, now we can start looking at what is a sampling distribution. So suppose we take one sample from our f of x population. Now, if we consider our sample mean from that one random sample, let's call that x1 bar. Now, in this black line, let us assume this is the spread or range of our data. Our true population mean, mu, is going to be in the center. We can notice that our sample mean from our one random sample isn't exactly at the true mean. It's a little bit to the left. But now, suppose, backing up, so we know that our statistics x bar is a random variable. So now, if we suppose that we take a couple random samples from our population, so say we take 5 random samples and we calculate those sample means, we can notice that it'll take on different values depending on which specific sample that we took. This makes sense. We take 5 random samples, and our results are not going to be identical. So now we can see where we have, say, 2 of our samples almost exactly at our population mean, 2 of our sample means are to the left, 1 is to the right. Now let's suppose we do it again. Well, at this point, we can notice that computed values occur according to some probability distribution. If we notice, as we've taken more of our, well, that was probably a little too high, but as we've taken more samples and calculated the average of those samples, we've started to get a distribution that looks like the normal distribution. And that is not a coincidence. At this point, let's take a look at a motivating example just to put it in a little bit more realistic terms. So suppose we have data from all 3,945,102 live births in the United States in the year 1998. We let one variable be birth weight, and we're going to have this in grams. Our mean birth weight is 3,318.9 grams. For those of us who grew up not using the metric system, that's about 7 pounds 5 ounces, and we're going to have a standard deviation of 609.5 grams. And again, for those of us who have grown up with the metric system, that's about 1 pound 6 ounces. And if we were to look at a histogram of this data, we can see that it approximately follows the normal distribution with most values clustered around the mean, and then it spreads out from there. Now, to kind of get an idea, so that was what we just looked at was our population. Now, suppose, for example, we take 10,000 samples of size 100. So meaning we take 10,000 samples and each of those samples have 100 observations. For each of those samples, we calculated the sample mean. Well, for our average of our 10,000 samples, the mean was 3,318.9, and we had a standard deviation of 60.9. If we scroll back up, we can see that our mean was approximately equivalent. Actually, it might be equivalent. It was. But what wasn't equivalent between our population and our sample was our standard deviation. This brings us to our second objective, to talk about the sampling distribution specifically for our sample mean. And it will explain why there was that difference in the standard deviations. So suppose we simulate a random samples from a known population. We then compute our sample statistics, X bar, for each of the generated samples. The statistics X bar is a random variable and thus will have a probability distribution. This distribution is called the sampling distribution. We want our sampling distribution to be centered at the mean, the population mean that is, and we wish for it to be unbiased. And we want the variability to be as small as possible. So looking at the sampling distribution of our sample mean, we'll consider the population f of x with mean mu and variance sigma squared, or standard deviation sigma. If a random sample of size n is taken and our x bar is computed for the sample, then theoretically our expected value of x bar, our sample mean, should be equivalent to the population mean. That's what we saw in our motivating example. Our sample mean and our population mean were equivalent. However, the variance of our sampling mean, the x bar, is equal to sigma squared over n. Now sigma squared, that's our population variance. So it's the population variance divided by our sample size. And our standard deviation for our sample mean will be sigma, our population standard deviation, divided by the square root of n. That's why we had, and I'll scroll back up to show you, why we had a difference between our standard deviations from the population to our sample distribution. Same means, different standard deviations. This leads us to now formally define what a sampling distribution of our sample mean is, assuming it's for our normal population. So when taking samples of any size n from a normal population with mean mu and standard deviation sigma, then our sample mean will approximately follow the normal distribution with mean mu and standard deviation sigma over the square root of n. That is, if x follows the approximate normal distribution with mean mu and standard deviation sigma, then its corresponding statistic, x bar, takes on values that will also follow a normal distribution, again, with mean mu and standard deviation sigma over the square root of n. And this is going to be true for any value of n. Okay. So this now leads us to talk about the very important central limit theorem. Of all theorems in statistics, the central limit theorem is the most important. So what is the central limit theorem? When we take a large sample size of size n from any population f of x with mean mu and standard deviation sigma, then our sample mean is going to approximately follow the normal distribution with mean mu and standard deviation sigma over the square root of n. What that means, if x has any distribution, not just the normal distribution, with an expected value of mu and a standard deviation of x equal to sigma, then our statistic, the sample mean, takes on values that will follow an approximate normal distribution with the expected value of our sample mean equal to mu and our standard deviation of the sample mean equal to sigma over the square root of n. But this only occurs when n is large. Let's take a look at an example of this. Suppose we have a distribution of population of CEO salaries, and we can see that it is very highly skewed to the left. Well, this first example was only a small sample. So for us, now we'll take a look at a sampling distribution of our sample mean when we have a sample size of, say, 10. And this results from 100 samples. 1,000 samples, meaning we took 1,000 samples. Each of those samples, we recorded 10 salaries. Notice that it is still skewed, but it is now less skewed than it was before, and we have more information. If we do this again with a sampling distribution of x bar, this time with our sample size being 50, meaning we are still asking that 1,000 people, or 1,000 people, whoo, flip back, we are still collecting 1,000 samples, but each individual sample, we are collecting 50 salary information of our CEOs. We can notice here, we're still a little bit skewed, but not nearly as skewed as we were before. It's starting to become more unimodal and symmetric. And now at this point, we'll do it one more time. We'll take a look at still taking 1,000 samples. This time, each of those 1,000 samples, we had an individual sample size of 100. Now, at this point, I wouldn't even classify our histogram as skewed, but both definitely unimodal and symmetric. It looks pretty approximate to the normal distribution. And that is an illustration of what the central limit theorem does. If we do this again with a second example, suppose we have a sampling distribution of our sample mean with a sample size of 200. And again, we're still doing a result of 1,000 samples. Again, sample size of 200. We're still looking pretty unimodal, symmetric. This clearly follows the normal distribution. So this begs the question, what value of n is going to be large enough? So if we scroll back, we had a sample size of 200. That was large enough. Sample size of 100 looked large enough. But when we were looking at, say, 50, 10, and even smaller than that, it did not follow the normal distribution. So that asks us, what value of n is going to be large enough to give us that approximate normal distribution? Well, most textbooks are going to tell you 30 is sufficiently large enough. Truthfully, that value actually depends on how skewed the data in the population was to begin with. But you're learning, so for you guys, you can stick to if it's about 30 or larger, you can say the central limit applies. But in the real world, in real practice, that's not really the case. I do want to caution you though, so we do need to talk about how the large N or our large sample size does not imply that the population somehow becomes magically normal. If the population was not normal to start with, taking a large sample will not change those results. It has to already be normal, but when we are taking those small samples, we're getting a skewed result. It's kind of the less information you have, the more inaccurate your inference may be. Our distribution of our sample mean is approximately normal if the true population is. Now this brings us to our last objective, and that's to use our central limit theorem to find probabilities about our sample mean. So we've now spent a lot of time talking about the theory and kind of giving you an example of how the central limit theorem works as we increase our sample sizes. Now let's put this into practice. So how in your careers or moving forward, you're actually going to apply the central limit theorem. So let's take a look at an example. So shower times are normally distributed with a mean of 11.4 minutes and a standard deviation of 2.7 minutes. A hot water system is adequate for 81 guests and the mean shower time is less than 12 minutes. A hotel currently has 81 guests. What is the probability that there will not be enough hot water? Okay, so we'll have x, and we will say that it will approximately follow the normal distribution. with a mean of 11.4 minutes and a standard deviation of 2.7 minutes. And we have a sample size of 81. We are asked to find that the probability of X bar, our sample mean, is greater than 12. So meaning the average guest spends more than 12 minutes in the shower. Using our knowledge of sampling distributions for the sample mean, this means that X bar will approximately follow the normal distribution with a mean equivalent to the population mean of 11.4, but we do need to adjust that standard deviation. So instead of being 2.7, it's going to be 2.7 divided by the square root of n, which is equivalent to 81. So this is going to be equivalent to our, whoops, I realized I made a typo there. That should not be a tilde, that should be X bar. So our sample mean will approximately follow the normal distribution with mean of 11.4 and a standard deviation of 0.3. At this point, this should become very familiar territory to you because now we can calculate our z-score of x minus mu divided by sigma. So plugging in 12 minus 11.4 divided by 0.3, and this will be equal to 2. So the probability of our sample mean being greater than 12 is going to be equivalent to the probability of z being greater than 2. We know that the normal distribution table gives us z less than or equal to z, so we need to use the complement rule and find 1 minus the probability of z less than or equal to 2. And this will be equivalent to 1 minus, so we need to find 2 in our standard normal distribution table, or our z table. I'm going to go ahead, pull that up because I haven't done that in a while. So we are looking for 2 exactly. So 2.0, that's going to be 0.9772. Going back to our slides, so 0.9772, so that's going to be equal to 0.0228. So in other words, there is a 2.28% chance that the hotel is going to run out of hot water for their guest. That's pretty good because I know if I'm in a hotel, I definitely want a hot shower. Okay, so let's take a look at a third example now that we've finished our second one. So for our third example, suppose for a particular community, it is known that the mean amount of water used per home during October is 1,250 gallons and has a standard deviation of 325 gallons. The distribution for amount of water used is skewed to the right. We can see this visually with our y-axis showing the density and our x-axis showing the amount of water in gallons. Leading us now to the actual question part of our example. So for a promotional campaign, a radio station plans to randomly select 50 homes and pay their water bills for the next month of October. What is the approximate sampling distribution of the sample mean amount of water used for a random sample of 50 homes? So we let X be the number of gallons of water used per home. We know that X is approximately skewed right with a mean of 1,250 and a standard deviation of 325. Since N is large, because it's larger than, say, 50, we can use our central limit theorem. So our sample mean is going to follow the approximate normal distribution with a mean of 1,250. And again, we've got to adjust that standard deviation to be 325 divided by our square root of n, which is 50. Simplifying, we will have our sample mean following the approximate normal distribution with a mean of 1,250 and a standard deviation of 45.96. So at this point, we have all the information we need to now answer the question, what is the probability that the sample mean amount of water is used less than 1,100 gallons? So again, from the previous slide, we know that our sample mean follows the approximate normal distribution, and we are asked to find the probability that our sample mean is going to be less than 1,100 gallons. At this point, we'll plug into our z-score formula. So z equals x minus mu over sigma. This will be equivalent to 1,100 minus 1,250 divided by our adjusted standard deviation of 45.96. If we plug this into our calculator, this would equal negative 3.26. Now, by looking at this z-score being so large, I can tell you that our probability is going to be small. Because if we recall to our 68, 95, 99.7 rule, 68% of our information is going to fall within one standard deviation, 95% is going to fall within two standard deviations, and 99.7% of our data will fall between 3 standard deviations. So this is actually outside the bounds of that 3 standard deviations. So this tells me this event is very rare. But you don't necessarily need to take my word for it. Let's calculate it and see if my logic is correct. So the probability of our sample mean being less than 1,100 is going to be equivalent to the probability of z being less than negative 3.26. If we go to our z table, we're going to be looking for negative 3.26, scrolling up. Well, that's not even, oh yeah, it is. I was saying it wasn't on my table because I was looking for negative 3.6, not negative 3.2. So negative 3.26. So that is 0.0006. Well, I was right. That is pretty rare. So what is the probability that the sample mean amount of water used is less than 1,100 gallons? Well, about 0.06%. In other words, very small. Let's take a look at another example just to wrap things up. So the random station can afford to pay for a total of 69,000 gallons. What is the probability that the total number of gallons for a random sample of 50 homes will exceed the 69,000 gallons? So we want to know what is the probability that the total is going to be greater than 69,000. This is going to be equivalent to the probability of our sample mean being greater than 69,000 divided by 50. Because again, 69,000 is the total. We're looking at 50 homes. So sum divided by our total will give us our sample mean. So we really are asked to find what is the probability that our sample mean is going to be greater than 1,380. At this point, we can now plug into our z-score formula. So 1,380 minus 1,250 divided by our adjusted sample standard deviation. And this will be, or not adjusted sample standard deviation, our adjusted standard deviation. And this is going to be equivalent to 2.86. Now at this point, it's just a matter of simplifying and using our z-table. So the probability of our sample mean being greater than 1,380 is going to be equivalent to the probability of z being greater than 2.83. Of course, our z-table does not give us greater than probabilities, but it does give us less than. So we really need to calculate 1 minus the probability of z less than 2.83. 2.83 in our z-table is going to be 0.9977. So 1 minus 0.9977 is going to equal 0.0023, which is thankfully pretty small. This means that the probability of our total exceeding the 69,000 gallons that the radio station can afford is 0.23%. So hopefully the radio station should be okay. Now, so we finished the problem, but let's just take a minute and think about some things. So suppose the total did exceed the 69,000 gallons. So therefore, in this sample, our sample mean would have been greater than the 1,380. So if we recall, we are assuming that our true mean is 1,250 for this scenario. And we found that the probability of our sample mean being greater than 1,380 to be only 0.23%, but this is while we were assuming that the true mean was 1,250. So that would have meant that either the sample we took was an extremely rare sample, or that the true mean was not actually the 1,250, which can happen. These are low probability events. It would be more likely that we took a rare sample, or would it be more rare that the true mean is not really equal to what we think it is? I'll leave you to think on that. Now, let's talk about evidence against our assumptions. So in our example, since there was only a 0.23% chance of taking a sample that resulted in a sample mean value greater than 1,380, if the true mean was 1,250. In such calculations, if the chance is 5% or less, we consider that to be strong evidence against the assumed value of the parameter of interest. This idea of if there is a 5% chance or less, that we consider that to be strong evidence against the assumed value of the parameter of interest. This is an important concept that we will use in both hypothesis test and confidence intervals, which is really going to be our main focus of the last half of this course. At this point, let's go ahead and review everything we did in this lecture. So first, we learned that X bar is a statistic, also known as the sample mean. We learned that if X approximately follows the normal distribution with mean mu and standard deviation sigma, then the sample mean will also approximately follow the normal distribution with mean mu and standard deviation sigma divided by the square root of n. We also learned the very important central limit theorem, where if X follows any distribution with a mean mu and a standard deviation sigma, then the sample mean will approximately follow the normal distribution with mean mu and standard deviation sigma divided by the square root of n. And also we learned how to use sampling distributions to find probabilities about X bar. And although it's not listed on the summary table because it wasn't the main focus of the lecture, we talked about these last two slides thinking about what happened if our total did exceed that 69,000 gallons and what it would mean for us is an important concept for you to keep in the back of your head. I highly recommend reviewing these two slides at a later date. Okay, everyone, that brings us to the end of this lecture. As always, if you have questions, please send me an email. Have a good night.